Okay, when we started each unit, when we started linear equations, and then when we started quadratics, we had those pattern sheets. And we took the patterns and we counted the boxes, and then we made a table out of them. Do you guys remember that? So that's what we're gonna do today, is we're going to look at visual patterns of exponential functions. So you should have like read over your definitions for exponential functions and know the difference between exponential growth and exponential decay. So growth is whenever something gets bigger, right? And decay is when what? Something gets smaller, right? Okay, so we're going to look at these patterns. It says, how is the pattern growing? So I want you to draw the very first bacterium, and then I want you to draw the 3 that it creates after an hour. And I'm okay with you guys just drawing circles for this, instead of, you don't have to like try to draw it exactly the way that it is up there. So it says, there are some bacteria in a dish. Every hour, each bacterium splits into 3 bacteria. The diagram shows the bacterium in 1 hour and 0 hours. So this is 0 hours, right? And this is 1 hour. So 1 bacteria split into what? 3. So after the next hour, what do you think is going to happen? So I'm just going to have 3 more. So one of these is going to create what? 3, right? And then another one is going to create 3. And then another one is going to create 3. So how many do we have now? How many is that? You got 3, 3, 9. Good. So after we first started with 1, then after an hour we have 3, and now we have 9, right? And this is after 2 hours. Do you guys remember how to draw the, like a table for this? So the hours go in for X, and then Y is the amount, right? Okay, so after 0 hours, how many did I have? 1. Good. After 1 hour, I had 3. After 2 hours, I have 9. And then after 3 hours, how many do you think I have? Yes, he's right, 27. Because look how much it's going up each time. Like if you're at 1, how do you get to 3? You can add 2 or you can times it by 3, right? But then you look at the next one, from 3 to 9, how do you get there? Can you add 2? No, so we're multiplying by what? 3 each time. So the next one, we would multiply by 3, and then what would we end up with? 27. So what pattern did you notice? So it's growing by a multiple of 3 each time, right? So it multiplies by 3. So in exponentials, you're always multiplying, but it's not always the same number. So after 2 hours, we had 9, and then we have 27. Do you guys remember how to recognize patterns of linear equations? linear equations, these numbers right here, your patterns, always add and subtract with linear. So write that down. So linear patterns always add or subtract. What about quadratic patterns? What do those do? When I did this for quadratics before, do you remember? I didn't get the same kind of number, right? How many times did I have to branch them off to get the same number? Twice. Good, because it's quadratic. So write down quadratic patterns. They have a common second difference. That's how you tell it's quadratic. So with linear, like it doesn't have a common second difference. So linear is always adding or subtracting. Quadratic patterns always have a common second difference. And then exponentials, what is the pattern that we noticed? Quadratic is the second difference, and then exponential patterns always multiply by a number or a fraction or a decimal, fraction slash decimal. You guys got all those? And that's why I wanted to go over the Tuesday's notes with you, because I always add stuff to the notes. Are you good with this? Good? Okay. So it's super important for you to remember all these different patterns, because our next section, we did linear, we did quadratic, we're doing exponential. And the next section is how can you tell the difference? So you have to look at tables and be able to figure out, hey, this is linear, this is quadratic, or this is exponential, just by looking at tables and graphs. So linear patterns, what kind of lines do those make on a graph? Straight lines or like parabolas? Straight lines, good. Quadratics make what? Parabolas. And then the exponentials make those little curves that we saw last week. All right, let's move down. Okay, so this is what it will look like when you actually drew out the bacterium. So Samoy, can you show your paper? Like she actually drew it out and colored it. So that's what it's supposed to look like. And that's how much it doubles. See how it's like, it's the reason that it's curved like that, the graph is curved on an exponential, is because it's like gradually growing, and then all of a sudden, look how many you have. It goes like straight up. That means the rate is greater. Does this look familiar? Because we've had one of these sheets before, right? Okay, so this is a different type of pattern, but it's the same kind of sheet that we're used to seeing. Like we had one for linear and we had one for quadratics. So I want you guys to, just on your sheet of notebook paper, just put hour 0, hour 1, hour 2, hour 3, hour 4. And then you can just draw the little bacteria. In this case, I'm drawing circles. So it says there are 3 bacterium in a dish. Every hour, each bacterium splits into 2 bacteria. This diagram shows how many bacteria are in hour 0, then hour 1. So what happens, like the first, at hour 0, you're going to create a table, right? This is the hour, and this is the amount. So create your table. 0, 1, 2, 3, 4, 5. I'm just writing it over so that you guys can see it clearly. After 0 hours, or initially, how many bacteria do you have? 3. After 1 hour, 6. What about 2 hours? 12. What do you think happens after 3 hours? Good, 24. Do you see why? It multiplies by 2, right? So after 3 hours, 24. So each time you're multiplying by what? 2, 2, 2. So after 4 hours, 48. And 5 hours, 96. So in words, the most important part of this table is that you want to put the initial amount is 3, and its growth rate is 2. And last week I showed you an equation that looks like this. This is what all your exponential equations look like. It's always to the x power. This is your starting number or your initial value. This is the rate or ratio. So if I wrote an equation, what was the initial value? What did we say it was? 3, good. What was the rate? 2. So before I spend my time graphing it, put this equation in Desmos. You guys still have Desmos? I'm gonna drag it over here. Am I gonna put the y in there? No, I'm gonna put the 3. Do I need parentheses? Yes. 2. You're gonna put parentheses around the 2. And then what's the exponent? Squared? Remember, your exponent is always what? X. Exponential exponent is x. And then you have that curve. So going from left, like over here to over here, it's going up, right? because the growth rate is 2. One of the questions was, what is the domain and range? Do you guys remember what domain and range mean? It's the same thing for every graph. Domain is the what? Good. Domain. And we write it like this, right? And range is the what? The y. Good. Good, Autumn. Heads up. All right, so if I'm looking at the domain, look at all the x values. That means you're focused on all of these x's, right? If the graph goes this way, remember it has arrows, and then it goes all the way up. Do we know how far it goes up? No, because we can't see, right? So it's going up, but we're going to put, it goes from negative infinity to positive infinity. You got that? Most of the time the range is going to be specific numbers, and then the domain is going to be all real numbers, which is negative infinity to positive infinity. All right, look at the range. Range is you're focusing on y, right? Okay. This line right here is where it can't go past. Like every little curved part of your exponential function right here, it can't go past this line. So on the y, so look at the y value, right? What y value can it not pass? 0. Good. So it starts at 0 and it goes all the way up to what number? We don't know. So what is it? Infinity. Good. Good job. Do you guys remember what that boundary line is called? It's a weird word, remember? Horizontal asymptote, remember? The boundary line. So you guys got that? And then we know how to put it in the graphing calculator. If it's exponential, what's the exponent? X. Good. If it's quadratic, what's the exponent? Dos. So you said? 2. Yeah, good. All right, let's scroll down. All right, let's look at this pattern. I'm sorry, it's small. Let's try to make it bigger. What do you guys want to do first? Do you want to count them and put them in the table, or do you want to try to draw them? Okay, you do what you think is best first. You guys know that you're looking at them as individual triangles, right? You're looking at the pattern as individual triangles. So you're counting, like in stage 3, how many do you have? Oh, not stage 3, stage 1, 3. Because it's each individual tile. I like counting them and putting them in the table because it's, to me, it's quicker. Do you guys feel like that too? Okay, so it's stage, so make your table again. So you have the stage number, and then you have the number of tiles, right? So tiles, stage, 0, 1, 2, 3, 4, 5. So what do we have at 0? A whole lot of nothing, right? 0. And then stage 1, 3, stage 2. Yes. Stage 3. Yep. So look at these. How do they increase? This should have a line, right? Because it should increase by what? 3. So if it increases by 3, right? So once we have 3, 3 times 3 is 9. 3 times 9 is 27. 27 times 3 is what? Good job. 81. 81 times 3. 200 what? 243. That's a lot to draw, right? Okay, so in words, where are you starting and what's happening? How's it growing? Okay, you start for nothing, like you start from 0, right? So the initial value is what? So the initial value is 0, and then it increases by a rate of 3. What do you think the equation would look like? Do you think I'm going to do this? Why? 0 is your initial value, but do you want to put that? Because what happens when you multiply anything by 0? It's just 0, so you don't want to include 0. So y equals 3 to the x power. So try to put that in Desmos. Make sure you guys know that the common rate sometimes doesn't have the parentheses around it. You see how I wrote it down when it didn't have the initial value? It's just 3 to the x power. So the rate always is to the x power. So does your graph look the same?
Yeah.
Yeah, it looks the same, but what's different? So your graph looks like, let's see if Miss Bolton can do this. Hold up. Like a curve, right? All right, you guys good with that? So the last example, we were multiplying by what? The common ratio was 2, right? And then this example, the common ratio is what? 3. Good. All right, let's look at, these are very similar. I definitely want to do this one with you guys. Okay, so if I did 1B, right, and I was looking at the pattern, how would you figure that out? What's the pattern? What are you multiplying by? Would you count first, or what would you do? Or are you looking at the difference first? You're going to count first? Okay, so step 1, how many? Next one? Next one? 16, right? Ooh. Four, 8, 16. Okay, so you can either do this 2 ways. You can think about it like X and Y, right? And a lot of you on your test, if you guys had a table that looked like this versus a table that looked like this, y'all were confused. You know that this is the same thing, right? Everybody's got that? This table horizontally is the same as this table vertically. So each time it's increasing by what? So 4 times 4 is 4 times 4, 8. So how much is it increasing by? Times 2, good. So it's growing exponentially by 2. What about this one? Are you guessing? Just because you have 3, don't just guess. So 1, 2, 3, yes. 1, 2, 3, 4, 5, 6. How many do you have over here? Okay, how much is that growing by? Yeah, so to get from 3 to 6, you have to do what? Multiply by 2? That looks like x squared, so I'm just gonna put a dot. And then 6 to 12 is times 2, right? Okay, so make sure you're counting them and then comparing them just like how I compared them. All of these patterns have like the same ratio. They're just like drawn differently. So your patterns can be the same, like it can have the same common ratio, like this pattern have 2 and this pattern be multiples of 3, but they're just drawn differently. All right, so look at these dots. You have pattern A and pattern B. Which one do you think is exponential decay, which means it's getting smaller? Pattern B, why? There's less dots. So this one would be, this is going to be exponential decay. So this is decay. And then all I want you to do for this one is just draw the table. You don't have to draw all the little dots. So then just do 0, 1, 2. So if this one's exponential decay, what is this one? Growth, because the number of dots is getting larger. So the same thing, draw the table. And then just count. So how many dots do you have over here? 18, good. How many do you have right here? 6, and right here? 2, good. And then here, 5, 10, 20. So you guys probably already know the pattern for A, right? What's the pattern for A? Multiply by 2. So if I was going to write an equation for this, what's the initial value? What do you start off with? 5, right? So my equation would be y equals 5. What's in parentheses? The rate or the common ratio, yes. So I put a 2 and then to the x power. You see where all these numbers come from? So 5 is the initial value. 2 is the rate or ratio, good. What about this one? Dividing by 3 is the same thing as multiplying by what? Do you guys know the answer? So dividing by 3 is the same thing as multiplying by 1/3. So because with exponentials, you're always multiplying, right? So you're multiplying by 1/3. And that's the same as dividing. I spelled dividing wrong. By so what would the equation for this be? Because I'm actually really multiplying by 1/3. What's the initial value? 18. And then where do I put 1/3? Into the x power, right? So I'm going to show you this shortcut just in case you ever get confused. If you're ever looking for the common rate and you're confused by the multiplication and the division part, you can always take the second number, right? The second number divided by the first number. So what's the second number? 10 divided by 5. What's that? 2. Is that your rate? Good. So look at this. I'm taking my second number, right? And I'm dividing it by 18. What happens when there's a smaller number on top? You get a decimal, right? Or you can reduce it. So you have 1/3. Do you see how I get that? So you can, that always works. You can always take the second number and divide it by the first number. So you can write that down too, and that will help you. So put find the rate by taking the second y value divided by the first. And that's just a shortcut. So not the first divided by the second, it's the second divided by the first. Do you guys understand why? Because that's the opposite of multiplying. You're trying to find the multiple. Got that? Okay, so there's a difference. I just want to show you the difference in the graphs. Just for this closing part. So one of our graph was 5 parentheses 2 to the x power. And you can do this with me if you want to. So it looks like this, right? That was my first one, right? This is that table right here. Watch what happens when I put this one in, the 18 1/3. So if I put 18 and then if you guys want to know how to put 1/3 in, you do 1 divided by 3. See how that worked? And that is to the x power. Why does that look so different? The two words are still on there. Good job. It's decreasing. So look at the red where it says growth. So going from, remember we read the graph from left to right? So going from left to right, it's going which way? It's up. So if you're like imagining that you're on a roller coaster and you start over here, you're going up, right? So the most left part of this blue line that's graphed, if you start up here, then you're going which way? Down. So that's decay. So decay, you're going down, because that would make sense, right? And then with growth, you would go up. So you got that? Okay, good. All right, so we are going to play a review game just on different parts of exponential functions where you guys have to identify parts of the exponential functions from last week. And we're going to do this on Kahoot.